Welcome to the session Matrix Spaces, Isometry Mappings and Homeomorphisms. Recall the notion of isomorphism between partially ordered sets. The corresponding notion in matrix spaces is known as an isometry. Definition: let X D1 and Y D2 be two matrix spaces. A mapping F from X to Y is called isometric if it preserves the distance, that is, D2 of f of x comma f of y is equal to D1 of x comma y for all x y in the set X. An isometric mapping f of x onto y is called an isometry. It is easy to see that an isometry is injective and that the inverse and compositions of isometries are isometries. Also, identity mapping from a matrix space to itself is an isometry. Examples: 1. Let A be a fixed point in Rn, then the translation f from Rn to Rn defined by f of x is equal to x plus a is an isometry. Also, the mapping f from Cn to Rn defined by f of z1, z2, etc. zn is equal to real part of z1, comma, imaginary part of z1, etc. real part of zn, comma, imaginary part of zn is an isometry. The reflection mapping f from R2 to R2 defined by f of xy is equal to minus x, comma, y is an isometry. The rotation mapping f from R2 to R2 defined by f of xy is equal to minus x1 sin theta plus x2 cos theta, comma, x1 cos theta plus x2 sin theta is also an isometry. 2. Let R be the real line and x be the set of all functions of the form f of x is equal to alpha x, where alpha belongs to R. The mapping d star from x cross x to R defined by d star of f comma g is equal to modulus of alpha minus beta, where f of x is equal to alpha x and g of x is equal to beta x for alpha comma beta belongs to R is a metric on x. Then the mapping T from x to R defined by T of f is equal to alpha, where f of x is equal to alpha x, comma, alpha belongs to R is an isometry. D of T of f comma T of g is equal to D of alpha comma beta is equal to modulus of alpha minus beta, which is equal to d star of f comma g, where d is the usual metric on R. 3. Let x and y be two matrix spaces having the same cardinal number and both equipped with discrete metric. Then any one-to-one correspondence between x and y is an isometry. There are several properties which are preserved under isometries. The next two theorems are immediate consequences of the definition of an isometry. Theorem: let x D1 be a bounded matrix space and y D2 be another matrix space. Let f from x to y be an isometry. Then y D2 is bounded. Theorem: let x D1 be a discrete matrix space and y D2 be another matrix space. If f from x to y is an isometry, then y D2 is a discrete matrix space. Theorem: separability is preserved under isometries. Proof: let x D1 be a separable matrix space and y D2 be another matrix space. Let f from x to y be an isometry. We shall show that y D2 is separable. Assume that A is a countable and dense set in X. Since f is bijective, f of A is countable. Let y be a point in y minus f of A. Then there exists a point x in X such that f of x is equal to y. Let epsilon greater than 0 be a real number. Then there exists a point x dash in A such that x dash is in S of x comma epsilon. Since f of x dash belongs to f of A and d2 of f of x dash comma y is equal to d2 of f of x dash comma f of x, which is equal to d1 of x dash comma x is less than epsilon, it follows that y is a limit point of f of a, and so f of a is dense in y. A metric space x d1 is isometric to a metric space y d2, written as x d1 is isomorphic to y d2 if there is an isometry from x onto y. The isometric relation is an equivalence relation in a set of metric spaces. Theorem: let A be a set of metric spaces, then the isometric relation is an equivalence relation. Proof: let xd be a metric space in A. Since the identity mapping I from x to x is an isometry, xd is isometric to xd, and so the relation is reflexive. Let x d1 and y d2 be metric spaces in A such that x d1 is isometric to y d2. Then there is an isometry from x d1 onto y d2. Now f inverse is an isometry from y d2 onto x d1. Therefore, the isometric relation is symmetric. Since the composition of isometries is an isometry, the transitivity is obvious. Thus, the isometric relation is an equivalence relation. In view of the above theorem, the isometric relation on any set A of metric spaces partitions A into equivalent classes. The following theorem may be used to transport the metric of a metric space xd to a non-empty set Y. Theorem: let x d1 be a metric space, Y be a non-empty set. Let f from x to y be a bijective mapping. Then there is a metric d2 on y such that x d1 and y d2 are isometric. Proof: the mapping d2 from y cross y to R defined by d2 of f of x comma f of y is equal to d1 of x comma y for all x comma y in x is a metric on y, as can be easily verified. From the definition of d2, f is an isometry from x onto y, and so x d1 and y d2 are isometric. Theorem: every isometry is a continuous mapping. The proof of this theorem is obvious. Theorem: let x1 comma d1 and x2 comma d2 be two matrix spaces, and A1 belongs to x1 and A2 belongs to x2. Then the mapping x1 to x1 comma A2 respectively, x2 to A1 comma x2 is an isometry of x1 respectively x2 onto the closed subspace x1 cross set A2 respectively set A1 cross x2 of the product matrix space x1 cross x2 comma d. Proof: let f from x1 to x1 cross the set A2 be a mapping defined by f of x is equal to x comma A2. Then f is onto, and d of f of x comma f of y is equal to d of x comma A2 comma y comma A2, which is equal to maximum of d1 of x comma y and d2 of A2 comma A2, which is equal to d1 of x comma y. Theorem: metric spaces xi comma di where I varies from 1 to n are separable matrix spaces if and only if their product matrix space xd is separable. Proof: assume that xi di for I equal to 1, 2, 3 etc. up to n are separable. Then for each I there exists a countable and dense set ai in xi. Then the set A is equal to A1 cross A2 cross etc. cross An is countable, and A closure is equal to A1 closure cross A2 closure cross etc. cross An closure. Since A closure is equal to x1 cross x2 cross etc. cross xn, conversely let xd be a separable matrix space. Let ai belongs to xi for I equal to 1, 2, 3 etc. up to n. Then the set A1 cross etc. cross the set AI minus 1 cross xi cross the set AI plus 1 cross etc. cross the set AN is a closed subset of X, and this closed subset is a separable subspace of X. By the above theorem, the mapping Fi from Xi to the set A1 cross etc. cross set AI minus 1 cross Xi cross the set AI plus 1 cross etc. cross AN defined by Fi of X is equal to A1, A2 etc. AI minus 1 comma X comma AI plus 1 comma etc. comma AN is an isometry. Since separability is preserved under isometries, Xi is separable. Example: Rn is separable since R is separable. Also, Cn is separable. Homeomorphisms. The inverse of a bijective continuous mapping need not be continuous. For example, consider the discrete metric on real numbers. Let R dash be this metric space. Then the identity mapping I from R dash to R is continuous, but I inverse is not. If a bijective continuous mapping F has the property that its inverse F inverse is also continuous, then F is called a homeomorphism. It turns out that a homeomorphism provides a one-to-one correspondence of open sets in domain and codomain metric spaces, and this one-to-one correspondence is responsible for some simplification in the study of metric spaces. We begin by making the definition of a homeomorphism precise. Definition: let X D1 and Y D2 be metric spaces, and F from X to Y be a mapping such that first one F is bijective, second one F is continuous, and third one F inverse is continuous. Then F is called a homeomorphism from X to Y, and X and Y are said to be homeomorphic, written as X is homeomorphic to Y. Examples: 1. The identity mapping from a metric space to itself is a homeomorphism. 2. The mapping F from R to the point minus 1 comma 1 where open interval minus 1 comma 1 is equipped with the usual metric defined by f of x is equal to x divided by 1 plus modulus of x for all x in R is a homeomorphism. Since modulus of f of x is less than or equal to 1 for all x belongs to R, the mapping f is well defined. Now, let y be any point in the open interval minus 1 comma 1. Then f of x is equal to y implies that x is equal to y divided by 1 minus modulus of y, which is in R. So, f is surjective. Also, f of x1 is equal to f of x2 implies that x1 and x2 are of the same sign, and modulus of x1 is equal to modulus of x2. Thus, f is injective. Since mappings x to 1, x to mod x, x to 1 plus mod x, x to x are continuous real valued mappings from R to R, and 1 plus modulus of x not equal to 0 for any x, the mapping x to x divided by 1 plus mod x is continuous. Similarly, the inverse mapping f inverse of x is equal to x divided by 1 minus mod x is continuous. Thus, f is a homeomorphism, that is, R is homeomorphic to the open interval minus 1 comma 1. 3. Any two non-degenerate open intervals a b and c d in R with usual metric on them are homeomorphic. Let f from open interval a b to open interval c d be a mapping defined by f of x is equal to a x plus b, where a and b are constants so chosen that f of a equal to c and f of b equal to d. That is, f of a plus lambda b divided by 1 plus lambda is equal to c plus lambda d divided by 1 plus lambda for each real number lambda such that lambda not equal to minus 1. Therefore, we choose a and b in such a way that the equality A into A plus lambda B divided by 1 plus lambda plus B is equal to C plus lambda D divided by 1 plus lambda holds for each real number lambda such that lambda not equal to minus 1. This gives A equal to D minus C divided by B minus A and B equal to BC minus AD divided by B minus A. With these values of A and B, F is bijective. Since F is a linear mapping, it is continuous. The inverse mapping F inverse of Y is equal to Y minus B divided by A is also continuous. Thus, F is a homeomorphism, that is, the open interval AB is homeomorphic to the open interval CD. 4. A matrix space homeomorphic to a discrete matrix space is sometimes called a discrete space even if its metric is different from that of the discrete matrix space. Theorem. The inverse of a homeomorphism is a homeomorphism. Theorem. The composition of two homeomorphisms is a homeomorphism. Theorem. Every isometry is a homeomorphism. The converse of the above theorem is not true. For example, the mapping F from R to the open interval minus 1 comma 1 defined by f of x is equal to x divided by 1 plus mod x for all x in R is a homeomorphism, but not an isometry. Theorem. Let x d1 and y d2 be matrix spaces and f from x to y be a bijective mapping. Then the following statements are equivalent. First one, F is a homeomorphism. Second one, a set G is open in X if and only if its image f of G is open in Y. Third one, a set F is closed in X if and only if its image f of F is a closed set in Y. Proof. 1 implies 2. Assume that F is a homeomorphism. Then F and its inverse F inverse are both continuous and inverse of F inverse is equal to f of G for any subset G of X. If G is open in X, then inverse of F inverse is equal to f of G is open in Y, that is f of G is open in Y. If G subset of X and f of G is open in Y, then f inverse of f of G is open in X by the continuity of f. Since G is equal to f inverse of f of G, G is open in X. 2 implies 3. Let f be a closed set in X, then x minus f is open in X and by 2 f of x minus f is an open set in Y. Since f of x minus f is equal to f of x minus f of f is a closed set in Y. Conversely, if for any subset f of x is a closed set in Y, then y minus f of f is open in Y. Since f of x minus f is equal to y minus f of f, by 2 x minus f is open in X and f is a closed set in X. 3 implies 1. Let f be a closed set in X, then inverse of f is equal to f of f is a closed set in Y. Therefore, f inverse is continuous. On the other hand, let G be an open set in Y, then y minus G is a closed set in Y and y minus G is equal to f of x minus f inverse of G. By 3, x minus f inverse of G is a closed set in X, so that f inverse of G is open in X. Thus, f is a homeomorphism. Corollary. Let x d1 and y d2 be matrix spaces and f from x to y be a bijection. Then the following statements are equivalent. First one, f inverse is continuous. Second one, f of G is open in Y for each open set G in X. And the third one, f of f is a closed set in Y for each closed set f in X. The above theorem gives a one-to-one correspondence between the open sets in x d1 and y d2. When f from x to y is a homeomorphism, then an open set G in X is mapped under F to an open set F of G, and the open set F of G in Y is mapped by F inverse to the open set G. Thus, the open sets G and F of G are related by a homeomorphism. Due to this one-to-one correspondence between open sets of X and Y, it turns out that any property P which can be defined entirely in terms of open sets in X and which holds in X also holds in Y. Such properties as can be defined entirely in terms of open sets in a matrix space are known as topological properties. For example, the notions of neighborhood, closed set, closure, interior, exterior, dense sets, boundary, continuous mapping, etc. are topological properties. On the other hand, the notions of open spheres, diameter, bounded set, uniformly continuous are some examples that are not topological properties. The topological properties remains invariant under homeomorphism. Let me summarize the major points discussed in this session. Let X D1 and Y D2 be two matrix spaces. A mapping F from X to Y is called isometric if it preserves the distance, that is, D2 of F of X comma F of Y is equal to D1 of X comma Y for all X Y in X. An isometric mapping F of X onto Y is called an isometry. Let X D1 be a bounded matrix space and Y D2 be another matrix space. Let F from X to Y be an isometry. Then Y D2 is bounded. Let X D1 be a discrete matrix space and Y D2 be another matrix space. If F from X to Y is an isometry, then Y D2 is a discrete matrix space. Separability is preserved under isometries. Let X D1 be a matrix space, Y be a non-empty set. Let F from X to Y be a bijective mapping. Then there is a matrix D2 on Y such that X D1 and Y D2 are isometric. Every isometry is a continuous mapping. Matrix spaces Xi Di for I equal to 1, 2, 3, etc. up to n are separable matrix spaces if and only if their product matrix space Xd is separable. Let X D1 and Y D2 be matrix spaces and F from X to Y be a mapping such that first one F is bijective, 2 F is continuous and 3 F inverse is continuous. Then F is called a homeomorphism from X to Y and X and Y are said to be homeomorphic. The inverse of a homeomorphism is a homeomorphism. The composition of two homeomorphisms is a homeomorphism. Every isometry is a homeomorphism. Now you can try to answer the following questions. First one, prove that the only isometries of the real line R are f of x is equal to x plus a, where a belongs to R and f of x is equal to minus x plus a. 2. Let x d1 and y d2 be homeomorphic matrix spaces. Show that x d1 is discrete if and only if y d2 is discrete. Third one, let A be a dense subset of each of the matrix spaces x d1 and y d2. Let the identity mapping I from A to A be extendable to a continuous mapping F from x to y and also to a continuous mapping G from y to x. Prove that F and G are homeomorphisms and that F is equal to G inverse. Fourth one, show that a circle and an ellipse in R2 are homeomorphic. Now you can go through the following books for your further study. First one, Principles of Mathematical Analysis by Walter Rudin, McGraw-Hill Book Company, Auckland, 1985. Matrix Spaces by P.K. Jain and K. Ahmed, Narosa Publishers, New Delhi, 1993. Third one, Topology by J.R. Mungers, Prentice Hall of India, 1991. Fourth one, Introduction to Topology and Modern Analysis by G.F. Simmons, McGraw-Hill, 1963. And the fifth one, Matrix Spaces by B.K. Tyagi, Cambridge University Press, New Delhi, 2010. Hope that you have enjoyed this session. We will meet again with another topic. Thank you.